Welcome to the blockchain voting revolution. In this talk, Dr. Microlearning explores how blockchain can transform voting systems by improving transparency, security, and trust. Over the next slides, we'll look at core mechanics, privacy techniques, pilot studies, legal challenges, and practical paths forward, using diagrams and case studies to make complex ideas easy to follow. At the heart of blockchain voting are three mechanics shown here: a distributed ledger that replaces central authorities and makes vote records immutable and time-stamped, cryptographic identities that prevent duplicate registration while preserving voter privacy, and decentralized tallying that removes middlemen and enables real-time audits without compromising anonymity. This diagram traces a voter's journey. A unique, non-transferable token links to a single voter. Smart contracts enforce the rules, votes travel as encrypted transactions, and everything is recorded on-chain immutably. The flow ensures one person, one vote, keeps ballots encrypted and permanent, and can use homomorphic tallying so totals are computed without decrypting individual choices. To protect voter anonymity while assuring validity, systems rely on cryptographic techniques. Blind signatures let voters obtain validated tokens without revealing identity to issuers. Ring signatures mix credentials into anonymity, sets to hide origin. And zero-knowledge proofs let a verifier confirm a ballot's validity without learning the voter's selection, balancing secrecy with verifiability. A national-scale pilot emphasizes tamper-proof tabulation. Accredited observers and distributed nodes record anonymized vote hashes in real time. An immutable blockchain ledger enables parallel tallying, and verification tools deliver official results within minutes. The visual illustrates how this architecture can demonstrate tamper resistance at scale and operate under constrained infrastructure. In a digital ID and permission chain pilot, residents received blockchain-based IDs and used a permissioned voting platform to cast non-binding referendum votes. The pilot reported 70% participant satisfaction, transparent and verifiable counting, and zero system downtime, leading to a decision to open source the stack and explore broader government collaboration. The Votes app pilot used biometric login and a private blockchain for overseas service members, counting 144 votes while shrinking turnaround from 45 days to 5 minutes and passing a post-election audit. Subsequent audits uncovered server-side vulnerabilities, underscoring that operational success still requires rigorous redesign and hardening of back-end systems. The central technical tension is the immutability-secrecy dilemma. Publishing raw votes boosts transparency but can threaten ballot secrecy. Proposed mitigations include off-view chain decryption keys to separate sensitive secrets, sharded ledgers to limit exposure, and mixed networks to obscure origins, while research continues on threats like mobile side channel attacks and smart contract bugs. Legal and procedural hurdles are substantial. Many jurisdictions lack statutory recognition for digital ballots, digital signatures, or decentralized tallying, and current recount and certification procedures assume paper. Moving forward requires updating election law, creating blockchain-specific audit criteria, and training poll workers so digital processes map to accepted legal and procedural standards. A practical near-term path pairs paper ballots with blockchain transparency. Paper remains the legal anchor, while QR-linked, anonymized tokens represent each ballot on one chain, enabling voter verification and auditor reconciliation. This hybrid approach offers immediate transparency, gains, and fallback redundancy, allowing trust to build gradually without forcing rapid legal changes. Widespread adoption depends on system hardening and open practices. Adopt open-source hardware security modules, common ballot token metadata formats, and mandatory third-party penetration tests, and pair those with continuous bug bounties, post-election cryptographic audits, and real-time public dashboards to educate voters and turn transparency into durable trust. University sandboxes accelerate learning by hosting testnet elections, sharing modular courseware and datasets, and piloting systems that can mature into mainstream use. This iterative cycle trains future election engineers, surfaces practical vulnerabilities early, and builds the collaborative resource base needed to scale secure, verifiable voting systems from experiment to deployment.